Welcome back to linear algebra. Let's jump into Anki. What is an elementary matrix? An elementary matrix is a matrix that can be obtained by applying one elementary row operation to an identity matrix. If an elementary matrix E results by performing a certain row operation on the identity matrix IM, how is the product EA related to the matrix A, assuming the product is defined? Assuming it's defined, it's basically the elementary row operation you use on I to get E will be the same elementary row operation you use on A. What must be true about the matrix A for the products A times the transpose of A and the transpose of A times A to be invertible? The product must be invertible. What does it mean to say that the matrices A and B are row equivalent? It's to say that they are basically the same size, and you can obtain one from the other by only using elementary row operations. Okay. On that note, where are we? What are we doing? Here we are. Yesterday we were doing stuff on matrix transformations. What were we doing exactly? A procedure for finding the standard matrix. The standard matrix is basically the matrix that's being multiplied in a matrix transformation. And so there's a two-step process to find the standard matrix. What is that two-step process? That two-step process is first, identify all of the or find the image of each of the standard basis vectors for a given the vector space, and then step 2, partition them together so that the resulting the image of each is partitioned as the columns of a matrix, and that matrix is now the that's what you call the standard matrix. Reflection operators. So the next section was on reflection operators. Operators are when a transformation goes from Rn to Rm, and N and M are equal. These reflection operators are basically mirroring a point or line over a line or plane that includes the origin. Okay. Matrix operators that map each point into its symmetric image about a fixed line or plane that contains the origin. Okay. All right, that's all I actually have. Pretty good. I'm going to continue reading now. I'll be back to recall what I learned in a little bit. All right, so I finished reading 1.8. What do we have left to read about? More operators. What do we have? So I finished reading about the reflection operator. I think I already described that earlier. The next one was projection operators, also known as orthogonal projection operators. And basically in R2, it's going to take points and move them onto the axes, reflect them onto axes. And in R3, it's going to reflect them, take the vector and put it on, reflect it onto a plane, an axis plane that contains the origin. I'm not exactly sure what orthogonal means, but that's part of it. And then rotation operator is basically, we only did it in R2 because R3 is more complex. We're going to talk about it later in the book, but R2 or rotational operators will basically move a point along the arc of a circle. So, and then the counterclockwise, the standard matrix for counterclockwise, known as the rotation matrix in R2, is cosine, negative sine, sine, cosine, I believe. Yep. Rotation operator in R2 and rotation matrix in R2. All right. Then I did the first problem, which was to find the domain and codomain of transformation A of x equals ax. I didn't know exactly. I put like freaking I put these vector spaces, but I don't know, maybe it should be like all real numbers, all real numbers, all real numbers, and all real numbers, all real numbers, something like that. The way I got this, I think, is the domain's going to be, I don't know if this is the domain, but I think it's going to be in R3 because this is a 3x2 matrix. So the vector matrix is got 3 height, and then if you multiply it by, what the hell? No, I did that wrong. Actually, no, not necessarily. I don't know. We're gonna have to find out tomorrow. And then I went to 1.5 to do a review problem. I'm gonna find the inverse of this tomorrow. These are all real numbers or something like that. I don't remember what the instructions were, but that's it for today. Talk to you tomorrow. See you.